Thank you for reminding me. So yes, it is recording now. Thank you. So that is negative. That is less than 0. And I'm going to be lazy so I can fit everything in. You'll notice that if I do the positive square root and -1, I get the same thing. And therefore, those 2 points are saddle points. So there is the general thing. So as you can tell, it's kind of an extension of the one variable stuff. It's just that solving it can be a bit more complicated. So any questions on this? So I'll do one more. As I said, there really aren't many in this section. So same thing, although really they're asking something different, which we'll get to when we get the answer. So here's the function we want to find and classify critical points. So derivative with respect to x. Derivative with respect to y, that's a 1 minus x quantity cubed in the second one. Set them both equal to 0. In this case, it's probably easier to use the second equation. So using the second equation, what has to be true to make that 0? So either y equals 0 or x equals 1. So this time put those into the first equation. So x equals 0, y equals 0, sorry. Y equals 0 gives us a really simple equation. Do x to 0. We get the critical point 0, 0. If I put in x equals 1, I get 2 equals 0. And so obviously nothing comes out of that part. So we just have the 1 critical point. And then we take the second derivatives. If I put in 0, 0, I get 2 times 2, so 4 minus 0. And both second derivatives are also more than 0. They're both 2. And so again, this is a local minimum. And I forget exactly what their Actual questions. Let me actually look. Give me a second. So it said the official thing, there's only a point, and it's minimum code. And then it says show, however, that f does not attain a global minimum at the point, which wouldn't happen or can happen if you're doing one variable. Even though there's minimum, there's only one critical point, global minimum. And easily see that when x really negative, it'll start getting really negative because you'll really positive, I mean, because you'll have y squared times x cubed basically, which will be bigger than x squared. Right, so d is equal to the fxx times the fyy minus the mixed one squared, yes. So any questions on this? And because I want to get to the next one, which has a part of it, I'll wait until tomorrow to ask if there are any other ones from this is 2.9 that you have questions on. So any questions on this? And you'll see what I mean in the next example. And here I'm not being explicit, but we always assume that the boundary is included, because if it wasn't, unless you're told explicitly, if the boundary isn't included, then there might not be a global maximum. So here's our region. That's a 3, 9. Then again, similar to Calc 1, so this is really just an extension. The first step is the same as for the last problem, which is we want to find critical points, because we know from Calc 1, the global minimum or maximum, if it's closed, will occur either at a critical point or on boundary. And the generalization is just in one dimension, the boundary is just the endpoints. Here it is those two whole curves. So we're going to have to check for that whole curve for where y is equal to 3x and where y is equal to x squared. Right. So we take derivatives again. So they're both equal to 0. Oh, bounded. Sorry about that. So the first step is just like the last one. We get the critical points. So we take the two partials, we equal to 0, and we solve. As with the last one, since both include both variables, we are going to solve for one in terms of the other and then plug into the other. And again, it shouldn't matter which, but for me, this top one is easier. Because the only way that's true is if y is equal to x. And if I plug that into the second equation, I get just whichever way I want to do it. So negative 2x plus 2 is equal to 0. So x is equal to 1. So we get the 1 critical point 1, 1. Okay. Since I'm going to try to fit this on the page, I'm going to leave off for a second that now we certainly have these 2 points. These are obviously bounds that we're going to look at, 0, 0, and 3, 9. So right now we have the 3 points, 1, 1, 0, 0, and 3, 9. But now what we have to do is plug in the boundaries. And for that, I'm plugging that back original function. So if I plug in y equals 3x, and I should really have an f here, I suppose. So I get that function. So on the boundary, this is what the function is. It's now only one variable. But we still want to go through. We need to find possible critical points. So we take the derivative, set it equal to 0, which gives us x equals 3, which gives us the point 39, which we already had as one of the corners. So it doesn't give us anything new. Plug in the other boundary, y equals x squared. And that middle one is cubed, of course. So on the boundary y equals x squared, we have the function x to the fourth minus 4x cubed plus 4x squared. Again, we want to find critical points. So we take the derivative, we set it equal to 0. Oops. That's a 4x, because I pulled out one of the x's. And that gives me 3, 9. So to make that more obvious, that's a 9. And same thing here, 9. So that gives us, if I plug that into, as I said, I'm trying to keep it all in one thing. If I put it, this gives me x equals 0. If I plug it in, that gives me 0, 0, which I already had. This gives me x equals 1, which if I plug in, I get 1, 1, which I already had. And if I put in 2, I get 2, 4. So at the end, we have lots of possible points. So the possible points, which I'll go to the next page and use, we have 0, 0, we have 1, 1, we have 2, 4, and we have 3, 9. Only one of those is a critical point. The other ones are possible points on the boundary. Oh, because, right, this gives me one of the possible places where the derivative of this is 0 is at 2. And I plug that back into what I plugged in, which is y is equal to x squared. So here's where now changes from the last one, which is we added this extra step for look to find out what's going on in the boundary. But the other is we don't have to take the second derivatives because we know, actually I might be able to fit on this page, we'll see. We know that the global minimum and the global maximum will occur either at, so I'll make it nice and messy, do this up here, either at a critical point or on boundary. So therefore, what I'm going to do is plug these into the, make it really messy, plug these points into the original function. So if I put 0, 0 into the original function, I get 0. If I put in, I'm doing this for a reason, 2, 4, I also get 0. Although you'll double check my numbers. If I put in 1, 1, I get 1. If I put in 3, 9, I get 9. Okay, so the global maximum is just the biggest possible one. That's the biggest possible. So the global maximum for this function on with this restriction is 9. And the global minimum is the smallest possible, of which there are 2. So we can have more than one global minimum or maximum. So 1, 1 is nothing. So if the first derivative was 0, then maybe it would be the equivalent of like an inflection point, but here it's just, yeah. Okay, so this is really messily, but here is the setup for the full 2.10. So any questions on the steps? So we did one of these also on Thursday. Next thing is, as I said last week, what you should expect is we're going to do a word problem, which in some ways will be harder, in some ways will be easier. But if I do, I'm going to have you try one of these, something like this, on your own. So let me do the thing I've done the last couple of classes, which is let me share the problem, which is also on Blackboard. So if you go into course material, it's also going to be there. That way, if you have trouble seeing it, you can also see it there. So you can see this one's actually a short one. It's just one problem. But as you can see from the one we just did, one problem's fairly lengthy. So again, I can't control how you see it, but if you go into the line just below the top, you should be able to make it bigger so you can see it. Or as I said, if you go to course material, it's also there. And so here let me just start the drawing, which is find the global minimum maximum on the region. And this is just in some ways, which is going to be, some ways not too bad, in some ways a bit of a pain. So we're just looking at this region, just the rectangle, which means what are the boundaries that we're going to plug in once we start doing stuff? This is where as I said, it'll be a bit of a pain. We start, one of the boundaries is y equals 0. Right, and then y equals 3, and then x equals 0, and x equals 2. So what we're going to have to do is plug each of those into the original function. That's going to give you a new function in terms of one variable. You're going to have to take the derivative, set it equals 0, and solve. So as usual with these, the last couple ones, I'm going to give you 15 minutes or so. So try working on your own. If you have more specific questions, let me know. it's 2:15, so 2:30, 2:35, we'll start going over. And otherwise, unless you have a question, I'm going to shut up.